Thanks for joining us today. My name's Laura Knight, and I work in our employer partnerships team. And I'd like to introduce Mohamed Sedky.
Good afternoon, everyone. I am Mohamed Sedky, Associate Professor in our School of Digital Technologies and Arts, our Department of Computing, and I'm Associate Professor in Artificial Intelligence and Machine Learning. And today I want to take you through a journey for chatbots and language processing. And the main topic, which will be covering natural language processing building blocks. And so our aim today is to discover natural language processing and how it is important, including the application of natural language processing and how to build a natural language processing solution. So you might have heard about natural language processing and the relation between NLP and artificial intelligence and machine learning. So today we want to cover this relationship, and we want to see the building blocks of a natural language processing solution and how to build such solution using different platforms. And we're going to talk about words and how to separate a document into tokens, as we're going to call it, which are going to be words, and how to define the syllabus, prefix, and suffix, how to generate engrams, and how to build a stemmer, and then how to build our vocabulary using a tokenizer. So let's start by defining natural language processing, or NLP for short. So it is defined by a number of different definitions, but we are interested today into these three definitions. The first one is it is the automatic manipulation of natural language, like speech and text, by software, or it is the capacity of a computer to understand natural language that at level that allows meaningful interaction between the machine or the computer and the person. And the natural language processing, or the field of natural language processing, combines multiple fields together, including computer science, artificial intelligence, and computational linguistics. And this actually includes the interaction between computers and human, which is what we call it natural languages. So when we talk about artificial intelligence and the subcategory of artificial intelligence, which is machine learning, so we are talking about building an AI solution. And nowadays, building such a solution is not really a technology problem as such. It is a design problem. So most of you who will be willing to build a natural language processing solution, they might not be data analysts or experts in machine learning, and you don't have to be so, because you can actually, you got all the tools and the building blocks and the platforms which allow you to build such solution without being an expert in machine learning. So it is mainly nowadays, it's mainly a design problem, how to design a good solution for the problem you are tackling. And the AI is only as powerful as the data it is built on. And we see nowadays a new technique which is called deep learning, which is booming for the last 10 years or so, which made artificial intelligence and machine learning applicable and commercially valuable. And these techniques, we call them data hungry. So they are hungry for data. They need lots of data in order for them to build decent and elegant models. So machine learning algorithms allows us to perform multiple functions, including change detection and anomaly detection, classification, clustering, recognition, and regression or prediction. But today, one of our main application is natural language. Application of machine learning, of course, is natural language processing. And the application of natural language processing includes text processing and interfaces to databases or query languages, sentiment analysis, information retrieval, language generation, and expert systems for disease diagnosis, for some explanations, and chatbots, of course. So these are some of the applications for natural language processing. So let's introduce the topic. So in our class today, we want to learn how to split a document and any strings into discrete tokens of meaning, and this is what we're going to call it tokenization today. And our tokens are limited to words or punctuation marks and numbers, but techniques we are using could be extended to any other units and actually could be extended to other applications as well. And this could be extended to any sequence of characters like ASCII codes, for example, or emotions or emojis or mathematical symbols and so on. So we need to separate punctuations from words like quotes at the beginning and end of a statement, for example. And we're going to see techniques to do so. Once we have identified our tokens and in a document, then we would like to include in our vocabulary. So once you want to build a natural language processing solution, you need to make sure that you build the vocabulary suitable for such solution. We will return to the regular expression to try to combine multiple words with similar meaning in a process, what we're going to call it stemming. So today we want to cover these two processes, tokenization and stemming, in order to allow us to build a natural language processing solution. Then we will assemble a vector representation of our documents called a bag of words. And we're going to see two different representations. And we're going to see one of them, which will be the bag of words, which is the common representation used for natural language processing. So the main building blocks for our natural language processing solutions are tokenizer, parser, and stemmer. And if you look to the main components and the requirements for natural language processing is to follow the linguistics, which are the rules of syntax, grammar, which is a key natural language processing issue to make sure that we are following these linguistic rules, and to build what we call it context-free grammar, which is a list of rules which define the set of all well-formed sentences in a language. Then trying to segment our text into tokens, which is a process of tokenization. And of course, just having tokens, separate entities of words, this is not enough by itself, because most interesting natural language processing comes by connecting these cores rather than in isolated sentences. Hence, we need to connect these tokens together. So the parser will help us to understand a single sentence by syntax analysis, and the stemmer, which is a process of grouping the various inflections of a word into the same bucket or cluster. So these are the processes which we're going to need to go through in order to build an LP solution. So as you can see, I have added two examples, one using a platform called RapidMiner to the left, and to the right, one which is using Python programming language. And these two platforms will allow us to build a natural language processing solution. RapidMiner, we can, this what we call it, so we don't have to program using text programming. So this you can use using blocks. So you can bring blocks together and just identify the main parameters and define the main parameter for each block. And the other one is text programming called Python. So in RapidMiner, for example, you can use a tokenizer block, and you can have a stemmer block, and you have a number of different blocks to transform cases, for example, from upper cases to lower cases, or to filter some stop words and the like. For Python, you need to use some commands like split, for example, sentence.split, where it splits your sentence into what we're going to call it tokens and the like. So these are two examples, two platforms, which would allow you to build a natural language processing solution. So let us start by defining words. And I want you to think for a moment about what a word or token represents to you. And does it represent a single concept by itself, or some blurry cloud of concepts? And could you be sure, or you could always recognize a word or not? And are natural language words like programming language keywords that have precise definitions and a set of grammatical usage rules or not? So when, for example, in programming, when I say split for a sentence, does it mean the same thing exactly in natural language or not? So, for example, the word ice cream, for example, one word or two to you. So would you consider ice cream as one word or 2 words. And don't both words have entries in your mental dictionary that are separate from the compound word, which is ice cream? So whether ice by itself and cream by itself, each one of them has meanings. And if you combine both them together, have a different meaning. And what about the contraction don't, for example? Should that string of characters be split into 1 or 2 packets of meaning? And this the issues we're gonna face when we build our tokenizer. So when it comes to syllabus, prefix, and suffix, so words themselves can be divided into smaller, meaningful parts. But syllabus, prefix, and suffix like re, pre, ing have intrinsic meaning by themselves. And parts of words can be divided further into smaller packets of meaning. So we can divide the word itself into syllabus and different parts, and each part will have their own meaning. So what about invisible or implied words? So when I tell you, for example, don't, so what does this imply to you? Does this imply to you, don't you do that, or you don't do that? So this means there are hidden words. So I tell you don't, but you as a human, you understand it, and you add and you infer other words next to the word don't. So if you can force yourself to think like a machine and then switch back to thinking like a human, you will find that you might want the machine to be able to infer hidden words. Like when I say don't, so you want the machine or the computer to infer don't do something. Yeah, so there is a verb next to it and there is a subject, which is something is missing, but you as a human, you from your experience, you can add this information. So these 3 hidden packets of meaning for a total of 5 tokens you would like your machine to know about and to be able to add. This takes us to another term, what we're going to call it Engrams. And in this lecture, we will show you straightforward algorithm for separating a string into words. And we can extract pairs. So instead of just like ice cream example, for example, instead of just each word to be considered or to be extracted as a token, we can extract pairs to be extracted as 1 token, or triplets, 3 words together as 1 token, or quadruplets, so 4 words together as 1 token, or even quadruplets where 5 words can be considered as 1 token. And what we define here is called Engrams. So it could be 2 grams if we're talking about bigrams, or 2 or pairs of words, or triplets, 3 grams, 4 grams, quadruplets, and so on. So using Engrams will allow our machine to add to its vocabulary more meanings and more meaningful tokens, which will help to understand more our language, or our natural language. So for example, ice cream, which could be defined or could be extracted into 2 tokens, ice and cream, but you can define this ice cream as bigram, as 2 gram, and this to be added to your dictionary or vocabulary. Another 2 gram that you would like to keep together, Mr. Smith, for example. So your tokens and your vector representation, as we're going to talk about this vector representation of a document, will have a place which will have as part of its vocabulary will be Mr. Smith, as well as Mr. by itself and Smith by itself. And these will be 3 entries in your vocabulary. So like any machine learning algorithm, we need to perform what we call it feature extraction. So before you introduce your data to the machine learning model, you need to extract some features. So feature extraction can really retain all the information content of the input data in any machine learning pipeline. So it is very difficult to maintain and to keep all the information within your data, which you want to introduce to your machine learning model after feature extraction. So you're going to have to sacrifice some information. So that is part of the art of natural language processing, which is learning when your tokenizer needs to be adjusted to extract more or different information from the text for your particular application. And this is the main message we start with at the beginning. So the machine learning or artificial intelligence is not a technology problem anymore. It is a design problem. So you need to understand and you need to identify carefully the requirements of your application. And based on that, you can build your vocabulary and you can design your tokenizer in order to extract different information from your text which are suitable and relevant to your particular application. So in natural language processing, tokenization is a particular kind of document segmentation. So I'm giving a document to my tokenizer, and what I'm looking for this tokenizer to segment or separate words, or 2 words together, or 3 words, or 4 words, or 5 words, and I'm going to name the output of the tokenizer as tokens. But at the end of the day, the output of the tokenizer will be number of tokens. And this, what we call it, this separation is called segmentation. So this segmentation breaks up our text into smaller chunks or segments or tokens with more focused information content, which hopefully will pass it to other parts of our machine learning or natural language processing pipeline in order for us to understand this document or this sentence better, or for our machine, of course, to understand this sentence. So segmentation can include breaking a document into paragraphs, or paragraphs into sentences, and sentences into phrases, and phrases into tokens, which most likely going to be words plus engrams, which are going to be multiple words combined together, and on top of the words, punctuation. So tokenization is the first step in our natural language processing pipeline. So this is the first building block we are talking about today. So it can have a big impact, of course, on the rest of your pipeline. And a tokenizer breaks unstructured data. And there's a difference between structured data and unstructured data. So when it comes to machine learning, we differentiate between machine learning algorithms applied to structured data and machine learning algorithms applied to unstructured data. Unstructured data, including text, including images, videos, audio files, and the like, all these examples of unstructured data. On the other hand, structured data includes data which you can input into a table, like Excel sheet, for example. So when you can have multiple columns and multiple rows, and you have a fixed structure for your data, where you can fit the data into slots or into cells, this is called structured data. But this is not the case for natural language processing. This is not the case for text or images or videos or audio files, because you cannot put them into cells like this one. But machine learning algorithms are going to find it very difficult to deal with unstructured data. Hence, we need to convert our unstructured data to a structured format in a way or another. And this is what we want to learn in the next few slides. So our tokenizer breaks the unstructured data, which is a natural language processing text, into chunks of information that can be counted as discrete elements. And based on that, we can build a structure format where we can add these tokens into a table. And after that, we can introduce this table, which is now in a structured format, to our machine learning model. So these counts of token occurrences in a document can be used directly as a vector representing that document. So one way, which you're going to be learning in the next slide, is to count how many times we have seen each word on the document, and we can build a table, and we can add our vocabulary, which all the words we expect to appear in a document based on a certain application or particular application. And then if we put the number of appearance of the word in this document, so this by itself will be a structured format which could be presented to a machine learning model. Or alternatively, instead of putting how many times this token occurred or appeared, we can put whether it appeared as 1 or whether this word did, or this token did not appear, which is 0. So we can put 1 and 0 to represent the appearance of this token in this document, or the lack or the non-existence of this token in the document as 1 and 0. The simplest way to tokenize a sentence is to use white spaces. Of course, if you want to segment a sentence, you can just search for a white space, and you can assume that anything after this white space or before this white space is a token, and anything after this white space until the next white space is another token, and so on. And could be a space or could be in general a delimiter, which could be a comma, could be a semicolon, whatever you want to define as a delimiter. So in Python, for example, programming language, this can be accomplished with a standard library, which what we have seen in the previous slide, which is method called split, which is available on all string object instances, as well as the string built-in class itself. In RapidMiner, we can make use of number of different blocks, like tokenize non-letters, or tokenize linguistic, or filter stop words, or filter token by length. So we can specify certain length to make sure that a token has to be with this minimum length, or stem, which is a porter, what we can see by the end of this lecture, or transform cases, which can transform all our cases from upper letters to lower letters, or whatever we want to transform. Let's go through vector representations, which we use as part of our tokenizers. The first representation is called one-hot vectors. And these one-hot vectors are super sparse, as we're going to see in the next slide, which contains only one non-zero value. That's why it is called hot, which is non-zero value, which is 1. Yeah, and only one non-zero value in each row vector. So the columns of our of this vector representation will be all the vocabulary, so all the words included in our vocabulary, and each row represents a sentence. Represents again a token, or represents a word, and this word, whether it appeared or did not appear, and then based on that we can say that this sentence this word has appeared or not. So you can make that table of one-hot row vectors even prettier by replacing zeros with blanks. So this is the example here. Yeah. So as you can see here, so the top, the columns include all the words in our vocabulary, and then we can see that, for example, in this sentence, so Thomas appeared, and we can, if you replace zeros with blanks, so this means 26 did not appear, Jefferson did not appear, and so on. Yeah. And so on for the next one. So you can see it is only one which is will appear. So this is the first token, which is Thomas, for example. Second token, which is Jefferson. But as you can see, for the one hot vector, so this one hot vector includes all zeros, of course, all blanks now. Next to add, next to begin, all blanks or zeros, and only one token will be hot, will be presented, which is 1 in this case. And then the second token is began, and so on. So you can build now, or you can actually read your sentence now. Thomas Jefferson began, and so on. Yeah. So this is a way to represent your sentence using one hot vectors. Each vector will be represented a token, and will be only high or 1 or hot in one element or one token of your vocabulary. So you could also play a sequence of one hot encoded vectors back if you want to generate text, like what we have been doing now for a chatbot, for example, just like a player piano might play a song for a less artificial audience. Now, all you need to do is to figure out how to build a player piano that can understand and combine those word vectors, which is the one hot vectors, together in new ways. And based on that, you can tackle one of the main applications of natural language processing, which text generation. Ultimately, you would like your chatbot or natural language processing pipeline to play us or say something you have not heard before, so to generate new sentences using these one hot vectors. Imagine we got, for example, 3,000 books with 3,500 sentences each and 15 words per sentence. And this is a reasonable assumption of a short book. And that is a whole of big tables, matrices, which if you want to convert these sentences or these books into one hot vectors. So we are talking more than a million bits. So 10 to the power 12 bits. Even if you use a single bit for each cell in our matrix, and at 1 bit per cell, we need nearly 20 terabytes of storage for a small bookshelf of books processed using one hot vectors. So fortunately, we don't ever use this data structure for storing documents. We only use it temporarily in our random access memory, in our temporal memory, while our computer memory, while we are processing documents one word at a time. And we're going to see now another representation, which allows us to represent our documents or our books or sentences into much more compressed way, which is what we call it bag of words. So if we split our documents into much shorter chunks of meaning, say, for example, sentences. So what if we assume that most of the meaning of a sentence can be gleaned from just the words themselves? So let's assume that we can ignore the order and grammar of the words and jump them all up together into a bag. And this is what we're going to try to do now, using this one hot vector and combine them into a bag. So one bag for each sentence. And based on that, we're going to have much more compressed vector representation. So the most common use of bag of words vectors created this way is the document retrieval. So when we want to retrieve a document or searching, so we can use this bag of words. So how we're going to do that? So we can combine all this one hot vector for each sentence, and we can add all these ones together. And based on that, this will tell us, will give us how many times these words appeared in this sentence. So you can use this bag of words vector approach to compress this information content for each document into a data structure that is easier to work with. So if we sum all the one hot vectors together, rather than replaying them as they were, because they present, again, lots of storage required for this one hot vectors. But if we sum all of them together, now we have managed to compress them a lot. And based on that, we come up with bag of words. So for example, in this document, we have 71V, the example to the right, and 22 and, based on this summation, where we can add all the one hot vectors for all the sentences in our document. And based on that, we can see how many times or the frequency of appearance of the word the and to in trees and the like. So this is called word frequency vector. So this tells us how many times this word appeared in our vector, because it only counts the frequency of the word, not their order. We could use this single vector to represent the whole document now, or sentence in a single reasonable length vector, which is going to be much more compressed than the one hot vector. It would only be as long as your vocabulary size. So it's going to be, for example, if you got 10,000 words in your vocabulary, so it's going to be 10,000 length. And alternatively, instead of doing the summation of all one hot vectors, we can apply the logic OR operation. And based on that, this, instead of giving us the frequency of the words, this will tell us whether the word appeared in our document or not. And we could ignore a lot of words that would not be interested in as search terms or keywords. And this would be fine for a search engine. And this is what Google is doing, and Yahoo and the like, when they do a search engine index. So they first filter for information retrieval system by looking for this bag of words vector, which is binary 1. So search indexes only need to know the presence or absence of each word in each document in order to help to find this document for you. So if we limit our tokens, for example, to 10,000, so our vocabulary includes 10,000 words, most important words in particular application, for example, we can compress our numerical representation for the example we had before, which 3,500 sentence book, down to 10 kilobytes instead of the 30 or actually 10 terabytes we have been seeing before, or about 30 megabytes to our imagery 3,000 book corpus. One hot vector sequence will require hundreds of gigabytes. Now, as you can see, this much more compressed one. I'm going to finish this class by going through the next building block, which is Parser and Stemmer. So in natural language processing, composing a numerical vector from text is particularly lossy feature extraction process. Lossy, which means that we cannot return back all the information we have lost, because this is very compressed one. So we cannot return back to all the amount of information we have lost. So it is lossy. So the bag of words vectors retain enough of the information content of the text to produce useful and interesting machine learning models, but it is lossy one. So we cannot return it back from our bag of words vector into our actual document. So the techniques for sentiment analyzer are the same techniques Gmail used, for example, to save up from a flood of spam that almost made email useless. So when it comes to stemming, which is grouping the various inflection of a word into the same cluster, so very small people spend their careers, very smart people, sorry, spend their careers developing algorithms and grouping inflected forms of words together based on their spelling. So for example, you want to remove verb endings with ing or ending, or you would have a stem called end and ing and as two different words. And you would like to stem the word running, for example. So, and this is one of the challenges here, because if you want to separate run from ing, you cannot separate run. You have to separate them as run, and then to get rid of this extra n, and then you separate it to ing. And the other challenge is sing, for example. If you try to use the same concept and put s as one word and ing as one word, you come up with it is not meaningful one. So, or imagine trying to discriminate between a pluralizing s at the end of a word, like words, for example, and the normal s at the end of words like bus or lens. Again, you're gonna end up with different meanings. So, do isolated individual letters in a word or parts of the word provide any information at all about the word's meaning? And can this letter be misleading? Of course, they can be misleading. And this is what our stemmer is trying to do, trying to find meaningful words from our extracted tokens. So in summary, today we have learned about machine learning, and one of the main applications of machine learning nowadays is natural language processing, and the building blocks for natural language processing, including tokenizers, which is segmenting our text into tokens, separating them into words and engrams, dealing with non-standard punctuation and emotion icons like social media posts, for example, building a vector representation of a statement using the one-hot vector and the bag of words, and compressing our token vocabulary with stemming. So thank you for listening today and watching this one. And this is a reference I've used for today, and I'm giving over to Laura. Thank you, Laura.
Thanks, Mohamed. Hi everyone, as I mentioned previously, my name's Laura Knight. I'm just going to talk you through some of the support that's available to businesses within the Innovation Enterprise Zone here at Staffordshire University. So I'm in charge of a project at the moment where we're offering free short courses to Staffordshire-based SMEs, including areas of artificial intelligence. So if you've enjoyed what you've heard today and think there may be some opportunity there for you to apply some bits into your business, please do get in touch. Our artificial intelligence course covers a lot of what Mohamed's just been speaking about, including chatbots, language processing, Siri and Alexa technology, as well as cyberbots. We also offer cyber security if you're looking for ways that you can better protect yourself and your business. Web computing, that looks at websites specifically. Amazon Web Services, which is more around cloud computing, and we also have a business course as well, managing leadership and performance. So if you are interested in any of those, my details will be on the last slide. Please do get in touch and I can talk that through with you. Next slide, please, Mohamed. We have further projects within the team, again for Staffordshire-based SMEs, including things around prototyping and new product development. So if there's anything that you were looking to improve or build, we can support you with that. We have transport, logistics and mobility. So that's looking at the greener movement of goods and people around the world. So again, if you have any links with those sectors. We have office space and a startup hatchery on site at our Stoke-on-Trent campus, and everyone that uses that has access to our specialist equipment as well. We also offer apprenticeships and a wide array of courses. And if you were looking to do any recruitment around student placements or anything like that, again, we can support you from start to end with that as well. If you're watching today as a large employer, we do also work with you, and we can support with things like Innovate UK bids and KTPs. Next slide, please, Mohamed. So details. So if you want any further details, please do email employers@staffs.ac.uk. We will be sending out this webinar as well. And you can find out more about the Innovation Enterprise Zone on our website /business-services. And this webinar is part of an ongoing series where we do try and run one once a week. So again, if you would like to look at the future webinars that we've got coming up, please do go on staffs.ac.uk /events and you can register your interest there.